This is Reigate College Maths, Year 2 Pure 6, and we're covering vectors. So there's not a great deal that's new in the vectors that you do in Year 2. We'll just look at a very quick bit of revision of the Year 1 vectors. So vectors, remember, are something that have both magnitude and direction. When you're writing your vectors, please try and remember to underline them. So you should be, something's a vector, underlining it like this. It'll be bold in the textbook, but it's a very good practice to try and get into the habit of underlining vectors so that you know what's a vector and what is a scalar. A scalar is something which is just a number, just has magnitude and no direction. Magnitude of a vector tells its size. It's calculated using Pythagoras. A unit vector in the direction of a particular vector is where we take our vector and we divide by its magnitude to get a vector that is 1 unit long. Remember that two vectors in the same direction are parallel, or two parallel vectors have the same direction. We can find the direction of a vector of the angle that the vector makes with the x-axis using Pythagoras. Sometimes you might be asked the direction it makes compared to the unit vector I. The unit vector I is the vector 1, 0. Yeah, so it's a unit vector in the x direction, and j is a unit vector in the y direction. So let's just look at this quick revision question. Given that a is equal to 5i minus 3j, work out the magnitude of a and the unit vector that is parallel to a. So for part 1, we're just going to say magnitude of a, I'm going to write it like that, is equal to the square root of the I component, so 5 squared, plus the j component, so minus 3, negative 3 squared, and that's equal to the square root of 25 plus 9, which is root 21. So then if we do part 2 now, the unit vector that is parallel to a, and we write that a with a little hat, a hat is equal to 1 over root, that's 34, not 41, not quite sure what was happening with my arithmetic there, 1 over root 34, 5 minus 3 multiplied by the vector, or we could write it in I and j form as 5 over root 34 I minus 3 over root 34 j. Okay, we're going to go over the page now, and one of the things that we do in the Year 2 work is we apply those ideas but in 3 dimensions rather than 2. So in 3 dimensions we use Pythagoras to find the magnitude of the vector again, and we can also find a unit vector in exactly the same way. So example 1, find the magnitude of 2i minus j plus 4k, which is a, and hence find a hat, the unit vector in the direction of a. So we're going to say magnitude of a is equal to the square root of 2 squared plus negative 1 squared plus 4 squared, which is, well, this is 4 plus 1 is 5 plus 16 is 21, so root 21. To find the unit vector, a hat we're going to write it either as 1 over root 21 times the vector A, 2 minus 1, 4, or 2 over root 21 I minus 1 over root 21j plus 4 over root 21k. For things like this, I think it's acceptable to leave the denominator of our fraction as a surd and not rationalize the denominator. But if you prefer to do that, you would write this as 2 root 21 over 21i minus root 21 over 21j plus 4 root 21 over 21k. So that's really just applying what we know about vectors in 2 dimensions to vectors in 3 dimensions. One thing that is a little bit new is that to find the angle of a vector in 3 dimensions with one of the coordinate axes, we can do this. We can say if the angle it makes with the x-axis is theta x, then cos of theta x is equal to the x component of the vector divided by the magnitude of the vector. Same thing for y. We get cos of theta y equals y over modulus of a, and same thing for z as well. So if we do that for example 2 here, find the angles that the vector a is equal to 2i minus 3j minus k makes with each of the positive coordinate axes to 1 dimension. So first of all, we're going to have to find the modulus of a. So modulus of a is equal to square root of 2 squared plus 3 squared plus 1 squared. Well, that's 4 plus 9 is 13 plus 1 is 14, so it's root 14. So we can now say cos of theta x is equal to the x component, that's 2, over the magnitude, which is root 14. And then we can say that theta x is equal to cos the minus 1, 2 over root 14. We normally give these angles in degrees rather than radians, so this is 57.7 degrees. Same thing for y. Cos of theta y is equal to negative 3 over root 14. So theta y is equal to 143.3 degrees. You might like to just pause and work this out for theta z, but I'm going to write it down now. So if you've paused and worked it out, you can check your answer. Cos of theta z is equal to minus 1 over root 14. So theta z comes out to 105.5 degrees. If you're giving your answers to 3 significant figures, of course you give this one as 143 degrees, this one as 105 degrees. Now these formulas are not in the formula book, so you do need to remember them. Okay, so let's just look at one quick geometric problem, and then we'll go on to a proof question and an application to mechanics as well. So this example 3, again this is an example from the textbook. If we've got 2 vectors that are equal and they're expressed in terms of vectors which are not parallel, so I, j and k are not parallel, in fact they're perpendicular, then we can say that on each side of this equation, the components in terms of each of those vectors must be equal. So we're going to compare coefficients of those vectors. So we're going to say compare coefficients. So for I, the I component, we have got 3 here. 3 is equal to P here. So P equals 3. For J, we've got P plus 2 is equal to minus Q. Well, we know that P is equal to 3 already, so minus Q equals 5, so Q is equal to minus 5, negative 5. And for K, we've got 120 is equal to 4PQ, PQR. So we know that we can divide by 4, so we can say 30 is equal to PQR, which is equal to, what is it, 3 times minus 5 times R. So R must be equal to negative 2. So we've used comparing coefficients on each side to find the values of P, Q and R. Right, that's it for this first video on vectors. We'll go on to look at 2 more examples in the next video.